Hello, my name is Aaron Poulter-Martinez. I'm giving the preliminary design review presentation for the Wings of Daedalus team. We're a part of SATCOM GMU. We're a club organization at George Mason University. I've broken this presentation into several subcategories. The first one is the team introduction, and then we'll go into the summary, then the ThinSat overview and its payload details, then we'll go into its integration and test overview, the mission operations, and then our mission scheduling. We've broken our team into three sub-teams, a software, hardware, and ground testing team. The software team will be focusing on software development and programming for the microcontroller, and will also be focusing on the implementation of the control algorithms for attitude detection and control. The hardware team will be focusing on the selection and implementation of hardware components such as the microcontroller, sensors, and magnetorquers. The ground testing team will be focusing on the development of the ground testing environment to create a magnetic field for the attitude control testing. This is our team diagram. Our faculty advisor is Dr. Peter Patrowitz. I'm the team lead, Aaron Martinez, and then we have team leads for each effort. For the ground testing effort, we have Landon DeCoit. For the software effort, the software lead is David, and then for the hardware effort, the hardware lead is Matthias Duffy. Here are the acronym and phrases that we'll be using throughout the presentation. Please feel free to reference them. So for our summary, we're going to go into the mission statement and the long-term goal for the organization. Our mission statement for this project is that SATCOM GMU will investigate the ThinSat's ability to manipulate its attitude at varying altitudes by utilizing the magnetorquers and control algorithms. Our long-term goal is to design a space glider and use the attitude control methods developed in this project in the long-term space glider project. For mission success, we want to meet three different criteria. Our first criteria is to collect and relay sensor data. The satellite must successfully collect and relay data to the microcontroller and the beacon. Our second mission criteria is that the satellite must detumble. The satellite must be able to stabilize itself after being released in a tumbling state through the B-dot control algorithm. And then our third mission criteria is that it has to be able to manipulate its attitude. So after the satellite is stabilized, the PID control algorithm will be utilized in the attitude detection control system to change the attitude of the satellite. Here's our design overview for the ThinSat. It will consist of a microcontroller. We intend to use the MSP430. This is required to receive input from sensors and run the B-dot and PID control algorithms, and to regulate the current through the magnetorquers, and then provide data to the built-in processor on the ThinSat bus. And then the magnetorquers will receive current, and that will create a magnetic dipole for attitude control. Then we'll have a light sensor that will provide data to the microcontroller for solar triangulation. And then we'll have temperature sensors to collect temperature data, and then two IMUs. The second IMU is to increase reliability of attitude detection. Here's our high-level design diagram. Inside the center, we have the microcontroller, and then at the bottom, we have the sensor array. And each sensor will feed data into the microcontroller, and the temperature sensor will also relay its information directly to the beacon interface. The microcontroller will then also relay information to the beacon interface and communicate with the serial interface. The microcontroller will also deliver information to the power delivery system that will regulate the amount of current going through the magnetorquers. For a ThinSat overview, we'll also go into the mission requirements. A lot of these are just mission constraints that are described within the ICD, so the total mass must be less than 280 grams, and the custom payload will only require access to two 100 milliamp power ports. All custom payload components for the experiment will fit into the designated area described in the ICD, and then the payload must be able to operate and be fully functional after put under strong forces and vibrations. The custom payload must be able to interface with the ThinSat bus through the header described within the ICD. We must have no more than 6 analog outputs and 2 digital outputs, and we'll also be able to interface with the ThinSat bus through one serial input and output. The satellite must be able to measure its attitude with reasonable accuracy. This is needed for the detection part of the attitude detection control implementation. The satellite must also be able to process sensor array data through the use of the microcontroller. This is needed to implement the control algorithms. We must have at least 3 different magnetorquers positioned along 3 different axes. This is what allows it to create the magnetic field to change the satellite's attitude. Here are the changes made since the proposal that we first put in. Additions made to the mission operation was to use the PID control algorithm to point the satellite solar cells towards the sun and rotate if it overheats. And this project was also initially accepted as a backup launch slot. It would be greatly appreciated if our seats were to be converted to a permanent launch slot. This is the electrical overview of our custom payload. The electrical components will be implemented with a custom PCB that will be designed and fabricated on the school campus. The devices that will be implemented are the magnetorquers, the microcontroller, the light sensor, the temperature sensor, and the redundant IMUs. Here's a more in-depth look at the electrical overview. We'll be having coils, and these coils, when we run current through it, will create a magnetic dipole. This magnetic dipole will then want to align with Earth's magnetic field. That will then turn the satellite and will change the satellite's attitude. We'll also be implementing redundant IMU. This will measure the rotation, acceleration, and magnetic field strength for the attitude detection and control. We'll be implementing 2 of them for greater reliability. The InvenSense MPU 9205 and the ADIS 16405 IMUs will be utilized. They both measure 9 degrees of freedom. MSP430 microcontroller will be used to implement the BDOT PID control algorithms. It consumes very little power and will utilize FRAM, which is magnetic memory, and works well in a high radiation environment. A sun sensor will also be used. We decided to use a 2D surface-mounted position-sensitive detection sensor that gives the direction of the light source as a 3-dimensional vector. LMT86 analog temperature sensor will be utilized. It operates at 2.2 volts and has a wide range of negative 50 degrees Celsius to 150 degrees Celsius. It has high accuracy of plus or minus 0.4 degrees Celsius. It will be placed near the window of the custom payload so we can measure the external ambient temperature of the satellite. All software developed for the ThinSat will have high emphasis on code reusability, low cost, and high levels of abstraction. The flight software will be written in C++ and will be compiled using the C++ 14 compiler provided for the MSP430 by Texas Instrument. We intend on using a real-time operating system, mainly FreeRTOS, to ensure that the control systems are responsive and will meet real-time deadlines. All the code will be broken into 2 parts, mission-independent libraries that will be mostly reusable, and mission-specific tasking code. This is our code diagram. From our code diagram, we actually break our code up into 3 different sections: hardware and mission-independent libraries for abstract classes, and control algorithms like PID. The hardware-specific set of code for interfacing with sensors and controlling specific microcontrollers. And finally, we have mission and hardware-specific tasking code for pulling sensors and running control algorithms, and so on. Here's our preliminary data usage. The purpose of these graphs is really just to show that we don't intend on reaching over the data limit. We mainly intend on having 18 bytes for our attitude data, and then 1 byte for the experiment and microcontroller status, 6 bytes to measure the magnet torque currents, and then 4 bytes for the temperature sensor data. This is all the data that we will be relaying to either the serial interface or to the beacon that we'll be able to access through the ThinSat dashboard. For the integration and test overview, we have different requirements that we want to make sure we meet. We want to make sure that we're able to replicate angular movement and microgravity and produce a magnetic field. And whatever we create, we want to make sure that it's sturdy and reusable for future projects. We want to make sure that it's functional and will be easy for us to test the different control algorithms that we intend on implementing. For our testing environment design, we intend on making a Helmholtz gauge and an air-bearing table. The Helmholtz gauge is a collection of coils that are aligned along each axis. When current is run through 2 coils that are parallel to one another, there will be near uniform magnetic field through these coils. We also intend on making an air-bearing table that is a spherical bow-shaped device that emits a stream of pressurized air through it. When a flat table attached to a hawser is then placed within it, it will then allow the platform to rotate freely. The satellite will be placed on that freely to rotate platform, and then that platform will be placed in the center of the Helmholtz gauge. That will allow us to create a reliable testing environment. This is our overview of the launch day procedure. The ThinSat will be released from a tumbling state 250 kilometers above sea level. The satellite will then measure its attitude with the sensor array, and then the microcontroller will interpret and feed that data into the control algorithm and the beacon, and then the microcontroller from the control algorithm will regulate the current through the coils that will then produce a torque on the satellite. We'll repeat steps 2 to 4 until the satellite will detumble, and then we'll manipulate the attitude to point the solar cells towards the sun, and then we will reposition the satellite whenever the temperature sensor detects overheating. Here's our preliminary mission scheduling. Here's the Gantt chart that we have designed. We believe that it is a very optimistic Gantt chart, and it has gone over a few revisions since the submission of the preliminary design review document. Thank you for your time.